Section 4.5, we're going to talk about isosceles and equilateral triangles. Whoops, I can't spell today. So some more special cases is really what we're talking about here. So an isosceles triangle is a triangle with two sides of equal length. The congruent sides of an isosceles triangle are called its legs. The third side is the base. The two congruent legs form the vertex angle, and the other two angles are the base angles. So if I have a triangle with two sides of equal length, the congruent sides are called the legs. So AB and CB are the legs. The third side, AC, is the base. Okay. The vertex angle would be angle B. It's formed by the legs. So that's the vertex. And angle A and angle C are the base angles. There we go. So we have a theorem here. Theorem 4-3. An isosceles triangle theorem. If two sides of a triangle are congruent, then the angles opposite those sides are congruent. So what we're saying is if I don't know anything about this other than that these two sides are congruent, I can then say, so given AB is congruent to CB, then I can prove, I can just state that angle A is congruent to angle C by the isosceles triangle theorem. So it's a quick way to find two angles that are congruent. Okay? Theorem 4.4 is the converse. If two angles of a triangle are congruent, then the sides opposite those sides are congruent. So now, given that these two angles are congruent, we can say that the sides are congruent also. Okay, so let's look at this a little bit further. So if I have a diagram that looks something like this, I'm going to call this A, B, C, and then I've got a line here called D, E. And if I'm told that angle A is congruent to angle C, and AD is congruent to DE. So, can I prove that AB is congruent to CB? In other words, is this entire line congruent with this entire line? Well, yeah, I've got congruent angles, so yes, by the last theorem. So A is congruent to C, so this big side is congruent to this big side. Can I also prove that angle A is congruent to angle DEA? Let me pick up another color. So angle A congruent to DEA. And yes, I can do that because AB or AD is congruent to DE. So using two sides and two angles and comparing them to each other in an isosceles triangle. Okay, theorem 4.5. If a line bisects the vertex angle of an isosceles triangle, then the line is also the perpendicular bisector of the base. So if I have an isosceles triangle and I have a line that bisects the angle up here, then I can also say that it bisects the base. So if I have a diagram something like this, and we'll call this ABC again, and if I'm given that these two sides are congruent, I now know it's an isosceles triangle, and I can say that A is congruent to C. And then if I say that BD is a perpendicular, is an angle bisector. BD bisects angle B. So I'm going to put that here. So because of that, I can do some calculations here. First of all, I've got 54 degrees here, given, and I want to find angle X. So angle A is 54 degrees. So I can say angle C is 54 degrees by the isosceles triangle theorem. And since BD bisects, I know that those two angles equal each other. So let's see what we can do. Angle ABC plus angle A plus angle C all have to equal 180. So angle ABC plus 54 equals 180. Angle ABC equals 72. And then to find x, since BD is a bisector, x has to equal 36 degrees. Okay, pretty simple stuff. I've got a couple of things called corollaries. A corollary is a theorem that can be proved easily using another theorem. Since a corollary is a theorem, you can use it as a reason in a proof. So I have two corollaries. Corollary to theorem 4-3. If a triangle is equilateral, then the triangle is equiangular. So this is a corollary to the one that says if two sides are congruent, then the opposite angles are. Now I'm adding if all three sides are congruent, all three angles are congruent. Conversely, if a triangle is equiangular, if all the angles are equal, then we can say that all the sides are equal. And this is, should follow pretty easily from the other theorems that we've talked about. And that's it for today.